The project was to study the heat transfer in different regimes of flow, and the group members are Isabella Gorse, Caitlin Sakachi, Luke Westland, and Hamil Curie. The motivation behind this project was to be able to understand heat transfer concepts so that we can explain it to a younger, inexperienced audience, such as high school kids, so they get a glimpse of chemical engineering as to what it is and if it is a career path they want to take in the future. So to determine the regime of flow in which the fluid is flowing, we need to calculate the Reynolds number for the fluid. In this formula, rho stands for the fluid density, v stands for fluid velocity, d stands for pipe diameter, and mu stands for the fluid dynamic viscosity. There are different ranges of the Reynolds numbers, which determines the different regimes of flow. The first regime of flow is no flow, where the fluid has no velocity. The second regime of flow is laminar flow, where the Reynolds number has to be less than 2,100. The third regime of flow is transition flow, where the Reynolds number has to be between 2,100 and 10,000. And the fourth case is turbulent flow, where the Reynolds number has to be greater than 10,000. So we expect that a higher velocity is going to be able to give us more energy that is available for transport in the system. That means that turbulent flow is the flow with highest velocity and is supposed to give us the highest heat exchange. So in our experiment, the way we calculate the Reynolds number is that we selected 3 hypothetical times. The first time was 11 seconds, second was 45 seconds, and the third was 120 seconds. And we had a constant volume of 2 liters because we used a 2-liter water bottle. So we knew the volume was constant. So we divided the volume over the hypothetical times that gave us a volumetric flow rate. And we divided the volumetric flow rate over the cross-sectional area, which gave us the velocity of the fluid. We then plugged that velocity in the Reynolds number formula. And these are the values that we got. The Reynolds number, the first Reynolds number for the time of 11 seconds was 10,242.8, which means the flow was turbulent. For the second case of 45 seconds, the Reynolds number was 2,503. That means the flow was transitional. And for the third case of 120 seconds, the Reynolds number was 938.744, which means the flow was laminar.
For the experiment, we assembled a rough imitation of a single-pass heat exchanger. To start, we cut 2 holes in the bottom sides of our bucket that were the diameter of our chosen pipe. We inserted our pipe through the aligned holes and added an elbow at the feed end. This elbow allowed us to attach a funnel that facilitated the transfer of water from our container to the pipe, while also being large enough to not restrict the flow rate. We filled the inside of the bucket with room temperature vegetable oil until the pipe passing through the bucket was completely submerged. For measuring the temperature changes from our experiment, we used a meat thermometer that was accurate to the first decimal place. We recorded the temperature of the water immediately as it left the piping, and we recorded the temperature of the oil that was in close proximity of the pipe right after the water exited. For running our different trials that modeled our different flow regimes we looked to test, we poured 2 liters of water through our system over different time intervals. This allowed us to dictate the flow regimes, such as laminar, turbulent, transitional, and twice for no flow, once to imitate both the laminar and turbulent flow time spans. As you can see in the video of our turbulent flow trial, we used a thermometer to collect the temperature values of the water immediately as it exited the pipe, and the vegetable oil directly next to the pipe. We used these values to calculate the temperature change of each fluid in each run, and we were able to compare the heat transfer efficacy of the different flow regimes. The experimental process was the same for laminar, transitional, and turbulent flow. And for the no-flow trials, we sealed off the exiting end of the pipe in order to stop the water flow and simulate a stagnant fluid. When looking at the results of our experiment, we see that the turbulent flow trial produced the largest temperature change in the vegetable oil of any of the flowing regimes. We also see that the no-flow trial that ran for 2 minutes resulted in a similar oil temperature change, but also had the greatest water temperature change since the water was in contact with the pipe for the longest period of time. Overall, we can see that the results we obtained mostly aligned with the results we expected, as the turbulent flow regime was most effective at lowering the temperature of the oil in a short time period, though the temperature change induced in the oil was matched by the 120-second no-flow trial. Thank you for watching our video. We surely hope that you learned something about flow regimes in heat transfer.